Hi grade 12s, we're on to our last topic of differentiation within AP Calculus. So far we've done the product rule, the quotient rule, the chain rule, we did the derivatives of ln and e, we did implicit differentiation, and finally we're at the derivatives of trig functions. Now the proofs of all these derivatives of trig functions are beyond what we cover, and so what happens in AP Maths is we are given this table on our formula sheet, and the only thing we are really tested is can we apply this knowledge. So this is the particular table that's given to you in your formula sheet, and it says function on this side over here on the left, and then it says the derivative on the right. And so basically we get asked questions, and trust me, they can get a little tricky, but we don't ever have to know how to derive the derivative. We can just use the table. So let's just read through this table together. So the derivative of sine is cos. The derivative of cos is actually negative sine x. The derivative of tan is sec squared x. The derivative of cosec is negative cot x cosec x. The derivative of sec x is tan x sec x, and the derivative of cot x is negative cosec squared x. Now it's pretty hard to imagine why that works out the way it does, and hopefully you'll carry on to a maths course where you can discover why that is true, because it's pretty cool. So let's just do a whole bunch of examples together. What I've done on the right hand side is I've just chosen the part of the table which we will need, because it's easy to have the table right there. I mean, it's on your formula sheet, so you do have access to it when you're doing these types of questions. So this question says determine the derivative of f of x equals sine of 5x. Now that means we're differentiating sine, so my outside function is the fact that I have sine of something. So there's my outside function. However, in this example there's an inside function, because it's normally you just do sine of x, but in this case it's 5x, and so there's an outside function and an inside function, and there's a moment there's an outside function and there's an inside function, we're going to have to use the chain rule. So what you're going to notice is that all these rules that we've learned so far, we kind of use them in all of these questions. So let's try. So f dash x, remember what the chain rule said. The chain rule said differentiate the outside function and leave the inside function alone. So the outside function is sine x. If I differentiate sine x, I get cos x, but leave the inside function alone. So it's 5x. So if I just use my color here, this is the derivative of the outside function. Leave the inside alone, differentiate the outside. Multiply by, differentiate the inside. And the inside is 5x, and 5x will differentiate to 5. So there we go. So if I just use my color here, this is the differentiation. We'll try that again. This is the derivative of the inside function over there. So this is the chain rule. Differentiate the outside, multiply by the derivative of the inside. Now, I wouldn't simplify this very much, but it just doesn't really look nice with the 5 at the end. So not that it really matters, I'm going to put that 5 first. Now this is a different type of chain rule. We've always thought of a chain rule as a power function, because it's a function within a function. So we've always thought about an exponent. So this is quite a new application of the chain rule for us. So it's possible that a trig function is the outside function. Okay, let's have a look at some more examples. Our second one here says differentiate y is equal to cos 2x. So exactly the same idea. My cos is my outside function, and the 2x is my inside function. So this is very similar to the sine one. So what I'm going to say is that y dashed in this case, y dashed is, and what does the chain rule say? It says differentiate the outside function, so cos x differentiates to negative sine x. So this is negative sine 2x. Remember, leave the inside function alone. Multiply by the derivative of the inside function, which is 2x, and so that's 2. So if I just color coordinate my answer here, this is the derivative of the outside function, whereas this is the derivative of the inside function. Now again, I'd probably rewrite that, really not mathematically different, just mathematically prettier if I write it like that. Cool, so that's us practicing the chain rule. Let's get on to something more interesting. This example says b, and it's x squared times tan 2x. So the moment I have a look at this, this must be the product rule. simply because I have a product of two functions, and just note that these two functions are completely unrelated, so it's not like I can simplify that product. So now we're going to rehash the the product rule. So that's function number 1 is x squared, and function number 2 is tan 2x. So let's get going. The product rule is a nice one. So what is y dash? Well, the product rule says differentiate the first function, so x squared differentiates to 2x, multiply by, leave the second function alone, so that's tan 2x. And then it says plus, leave the first function alone, so that's going to stay x squared, multiply by differentiate the second function. And tan 2x will simplify to sec squared. Now here's the only problem. Because this is tan 2x, it is now also a chain rule. So this tan is now the outside function, like we practiced in the previous two ones. This is the outside function. And this 2x is the inside function. So notice this is actually a chain rule within a product rule. So I'm just going to highlight this and go, this is the chain rule. So now if I go back, the chain rule says differentiate the outside function. So this is going to be sec squared, leave the inside function alone, 2x, multiply by the derivative of the inside function, and the inside function is 2x, so 2. So let me just color coordinate it. This is the inside function of the 2x, and the outside function is the sec squared. And don't forget to leave the inside alone. Now, can I make that a little bit neater? I could maybe, it doesn't change much, but this is 2x times tan 2x, and that would probably make this 2x squared, sec squared 2x. So pretty cool question. Generally, this being a product rule, but then once we got to differentiating the tan 2x, that was a chain rule in itself. So, pretty cool. Let's look at another one. Cosec squared the root of x. Now, personally, I prefer to write this. Now, let's just quickly debate this squared there. If the squared is there, it means the root x would be being squared. But because the squared is next to the cosec, what this means is it means that cosec, now I'm going to change root x to the half, just because I know I'm going to need to differentiate it, and that's all being squared. So in actual fact, I might actually change these to a square bracket, just so we can see the difference between the brackets here. So I would prefer to write it like that before I differentiate it, because it really helps me to see what's happening here. Now what's happening here is a chain rule, because you have to the power of 2. And the moment you have to the power of 2, that means that this is a function within a function, except this is a chain rule within a chain rule, because cosec itself is going to be an outside function, and x to the power of a half is an inside function. So if I try and label this the best I can, this is the inside function for the cosec. So that's the inside function. This is the outside function for the cosec x to the power of a half. However, this entire thing is the inside function for the fact that you are raising this to the power of 2, which is the outside function. So I'm hoping this is making a bit of sense. It's a bit confusing. So basically, let's talk through the answer, and I think that might clear anything up. So my outside function is the fact that you're squaring something. So the chain rule says differentiate the outside function. So bring down the 2, leave the inside function alone. So notice this is the purple inside function. So leave the inside function alone to the power of and subtract 1. So that just is just 1. So that's the derivative of the first chain rule. So that's the outside, and this is the inside function when you're looking at the first chain rule. Let me just clean up my green. So there's the outside and the inside. Now I'm going to multiply by the derivative of the inside, the purple inside. Now within the purple inside, my outside function is this cosec, and my table tells me that cosec differentiates to negative cot x. Now in this case it's x to the power of a half times cosec x to the power of a half. So that's the outside function. Multiply by the derivative of the inside function, which is this x to the power of a half. So multiply by the derivative, so that's a half x to the power of minus a half. So let's just talk through that again. This first term is the fact that you are raising to the power of 2. So you bring down your 2, leave the inside alone, subtract 1. So that's the derivative of the outside function. Multiply by the derivative of the inside function, but the inside function is another chain rule. So my outside function is cosec, and cosec differentiates to negative cot times cosec, and then my inside function was my x to the power of a half, which differentiates to that. Now, can this be written more simply? Absolutely it can, because there's a little bit of simplifying that can be done here. So for example, I've got a 2 here, and I've got a half here. So 2 times a half is 1. I've got x to the power of negative a half here, which I'm going to bring to the front. I probably wouldn't bother changing that to the bottom, because in AP Maths we don't care about negative exponents at all. So it's x to the power of negative a half. If I have a look at this, writing it more simply, cosec x to the power of a half and cosec x to the power of a half, that's cosec squared. So I would probably now go with the fact that I'm going to put this negative right in the front, so much easier, and then I'm going to say it's cosec squared of, you could say root x, I don't like exponents so much, so I think that looks a little bit prettier, times cot root x. So all I've done there is written these 2 cosecs as cosec squared and then the cot root. So not particularly, it looks a little bit more simple and pretty if we just neaten it up a bit. So that one is quite a cool one. Let's try another one. Question D. Question D says cot, which is definitely going to be an outside function. So there's an outside function. So this looks like the chain rule again. And my inside function is this 2 minus 3x to the power of 4. So this looks like a fairly simple one in that it's just a chain rule. It's not a chain rule within a chain rule or anything. And what is the rule? We'll differentiate the outside function. The outside function is cot. Cot differentiates to negative cosec squared. Leave that inside alone. So leave that 2 minus 3x to the power of 4. Multiply by differentiate the inside function. And the inside function, well, the derivative of 2 disappears. So it's minus 12x to the power of 3. So bring down the 4, subtract 1. So just to color coordinate this is my inside function derivative, and this is my outside function derivative. Okay, neaten it up a little bit. I suppose I can say negative times a negative is positive. So it's 12x cubed times, let me actually not use a bracket, times cosec squared inside function. Okay, so hopefully you're starting to get the hang of this. They really are quite nice once you get going. Okay, let's try question E. Okay, in question E, again, I would rewrite y with this sine 6x to the power of a half, just because it's easier to see. Now, I think this is going to be a chain rule within a chain rule, very similar to the one we did 2 examples ago. So this is a chain rule within a chain rule. And the reason why I say that is that, once again, you've got raised to the power of a half being your outside function. And you've got your inside function as your sine to the power of 6. Sorry, sine 6x, not to the power of 6. That's your inside function. So let's just start that. So the outside function is bring down the half, leave your inside function alone, which is sine 6x, minus 1 from the exponent. Multiply by the derivative of your inside. Now your inside function has an outside function of sine, and then an inside of 6x. So now if I continue, the derivative of sine is cos. So this is cos 6x multiplied by the derivative of the inside, 6x differentiates to 6. So if I just color coordinate that, that is the outside function's derivative, that's the inside. So I can neaten this up a bit. A half times 6 is 3, so this is 3 sine. You could take this to the bottom and make it positive, we really don't care. And then cos 6x. Great. Right, on to the next question, F. Interesting. This looks like it's a product because there's two functions multiplied together. There's a sine and there's a cos. They multiply together. I can't simplify them. I was hoping maybe I could simplify this a bit, but I can't. And so this looks like it's going to be a product. Now let's look at this 5/3. That 5/3 is just 5/3. It's not a function. So what I'm going to do is I'm going to rewrite this as 5/3 times sine of x cubed. And I'm going to think of this as function number 1. And then multiply by cos 2x. And that's going to be function number 2. Okay, now if I have a look at each of these within function number 1, because remember in a product rule, it's differentiate the first function. Now if I look at this first function, I think this is a chain rule. Because you've got a power of 3 being the outside function, and you've got sine of x being the inside function. Let me not use that one, let's use this one. This is the inside function. So let's just focus on that in our differentiation. Now, this is probably going to be quite long, so I'm going to move over. So, the rule says differentiate the outside function, which is the fact that you've got an exponent of 3. So I'm going to bring down my 3, and guess what? 3 times 5 over 3, the 3's cancel, and I get 5. So it's 5. Leave your inside function alone, so that's sine x. Subtract 1 from the exponent. So this is the outside function of function number 1. Multiplied by the derivative of the inside function, which is sine x, and that differentiates to cos x. So that's the derivative of the inside function. Now, why were we doing this? Well, we're in the middle of the product rule. So what's actually happened here is this entire thing is the derivative of function 1. Because remember, the product rule says differentiate the first function, multiply by, leave the second. So multiply by cos 2x, because that's function number 2. So differentiate the first, multiply by, leave the second. Plus, leave the first, so 5 over 3 times sine of x cubed. So this is the first function left alone. Multiply by the derivative of the second function. Now the second function is cos 2x, which in itself is a chain rule. It's a chain rule because my outside function is cos and my inside function is the 2x. So now that I'm going to differentiate that cos 2x, cos differentiates to negative sign, so this is actually negative sine, leave the inside alone, multiply by the derivative of the inside, which is 2x, which is 2. So again, to try and color coordinate, this is the differentiation of the outside function, this is the differentiation of the inside function. And what is this? This entire thing is the derivative of function number 2. Because remember, all of these chain rules we were doing were within the product rule, and the product rule says differentiate the first, multiply, leave the second, plus leave the first, multiply by the derivative of the second. So you just have to really keep your wits about you when you're doing these things. Okay, let's write this out a little bit more neatly. I really don't think it gets much neater than this, so I'm just going to write 5 sine squared x cos x cos 2x. We don't bother changing the cos 2x to something involving x because it'll get even messier. Now I've got a minus here, I've got a 2 and a 5 over 3, so it's minus 10 over 3 sine cubed x times sine 2x. And again, we don't bother changing the sine 2x, it just gets messier. So, sure, quite a question, lots to keep track of. Okay, let's have a look at G. G looks like our first quotient rule because I see division. So let us remind ourselves what the quotient rule says again. The quotient rule says, have we done the quotient rule yet in this example, in this question, in this video? No, I don't think we have done it. So let's have a look. The derivative of, well, at my top function, first of all, let's have a look. This is my top function, so I'm going to call this function number 1, or top function, doesn't really matter. And this is function number 2, which is bottom function. And the quotient rule says differentiate the top. Now sec differentiates to tan x sec x. So that's, fortunately, there's no chain rule here, so it's tan x sec x. Now the derivative of minus 1 is nothing. So basically the sec x gets differentiated and the minus 1 disappears. Okay, now multiply by leave the bottom, minus leave the top, which is sec x minus 1, multiply by the derivative of the bottom, and tan is sec squared x. So let's just quickly color coordinate this. So this is the derivative of 1. Tan x is the fact that we have to leave the bottom. This is the derivative of 2. And this first bracket is just the top function. So don't forget, however, that there's a denominator. So this is all divided by the bottom squared, which is tan squared x. Now again, not particularly easy to simplify here. So let's just maybe write it a bit neater. So this is tan squared x times sec x. I could multiply it here, so I could say minus sec cubed x plus sec squared x, because that's a minus sec x times that, and then a minus times a minus is a plus, so plus all over tan squared x. Now it would be nice if you could factorize out of tan squared x and cancel, but there's nothing particularly in common. There is a sec x in common, which you could take out, but starting to get a bit annoying then. So we'll probably just leave it as b. Great. So let's move on to another example of where maybe we can take the question a little further. So example 3 says, if f of x equals cos 2x over sine 4x, determine the gradient of the tangent at x is equal to pi by 3. Now this looks like a quotient rule, because I see a quotient which isn't very exciting, but okay. Now that's going to get quite messy. So my first port of call, which I probably should have been saying this whole time, and maybe I've missed some where I could have done some simplifying. But if I look at any of these, doesn't look like I could have done simplifying before. Can I simplify should always be my question in trig derivatives. Because if I can simplify a bit, differentiating becomes a lot easier. So let's have a look. Can you change? Now I see the reason why alarm bells went off here is that I saw cos 2x and I saw sine 4x. Now 4x is double 2x. So if you think of this sine 4x as sine double 2x, there's the trig identity that says sine twice an angle is equal to 2 sine that angle times cos that angle. Now, I only recognize that because I saw that there was a cos 2x and then there was a sine of double that. Now, notice I didn't bother changing the cos 2x because I want to do that. And so actually, if I first notice, I'm not saying f dashed because I'm first simplifying f. This basically becomes 1 over 2 sine 2x. Great. Now, that's not a particularly nice one to differentiate. So I'm going to leave the half and I'm going to change this to sine 2x to the power of minus 1. And now it should be fairly easy to differentiate. So the derivative would be, don't forget the half is not, that's not a product here because a half is not a function of x, it's just a coefficient. Remember, we only do product rules when we have a product of two functions involving x. We could do the product rule here, but a half would differentiate to nothing, which means it would cease to impact. So I'm going to bring down the negative 1, so I actually get 1 over 2. Leave the inside function alone, which is sine 2x, subtract 1. But this is a chain rule. The derivative of sine x is cos x, so that's cos 2x. But hang on, that's also a function within a function, so the derivative of 2. So this is a chain rule within a chain rule again. So let me just write this down. This is a chain rule within a chain rule. So notice that this here was my outside function, and sine 2x was my inside function. But within your inside function, there was its own outside function, and then 2x being the inside function. So let me just say that's the derivative of the inside. This is the derivative. Oh no, I shouldn't. That's the wrong color. So let me go back. This is that's the inside. Let me go back. This is the inside function. This is the outside function of the sine, and this whole thing here, that's the outside function. So I hope my colors aren't confusing you, but basically the outside function was -1, so bring down the -1, leave the inside function, subtract 1, and then multiply. Maybe I should actually go and put this yellow line under here to explain to you that this entire thing is the derivative of the inside function, which had its own outside and inside. Now, yep, I can simplify this a little bit, because this is 2 times -1/2, which is -1. Now, notice I'm not bothering taking this to the bottom, because actually this question wasn't for the derivative. The question was, can you determine the tangent at x is equal to pi by 3? Now, don't forget that we use radian measure, hence pi by 3, and literally it's just calculator work. So this is now 2 pi by 3 to the power of -2 times cos of 2 pi by 3. Now, the most important thing is to remember when you go into paper 1 of AP Maths that your calculator must be on radian measure. So you push shift mode, and then number 3 is degrees and number 4 is radian, so push number 4. And then you can just type this in and it'll give us an answer. And that answer for me was 2/3. So that's the gradient on this graph at pi by 3, which is the same as the gradient of the tangent. So really nifty question, but really, really important, that first question. Can I simplify? Of course, if you didn't simplify, you could have done the quotient rule and you would have got some huge mess. But then when you just sub in pi by 3, you'd get down to 2/3. The only reason why it's important going forward to maybe simplify first is if you were trying to draw this function and find stationary points, you don't want to be solving an equation with a huge, horrible derivative. Right, let's do our last example. So, not one that we're going to like much, because the question says the displacement of a particle is given by the formula s equals 1 plus 3 sine 2t, where s is in meters and t is time in seconds. Sketch the graph of s. So, oh my word, when last did we sketch a trig function? Especially in radian measure. So, I'm probably first going to need to draw a rough sketch. Now, it says from 0 to 2 pi. Now, especially when you're not used to radian measure, I always convert that to degrees in my head. So don't forget that pi is 180 degrees, so 2 pi is 360. Now, if I have a look at this, this is 3 sine. Let's just think about this in degrees. This is getting stretched by a factor of 3. So it's going to be ranging from 3 to -3. Oh, but just be careful, you also added 1. So actually, it's going to be ranging from 4 down to -2. Okay. Also have a look here that we are compressing this horizontally, because my period is going to be 360 degrees, which is 2 pi, but divided by 2, because everything's happening twice as fast. This is pi. So halfway between here, we should have 1 period. Now let's just, in grey, I'm just going to draw what sine would look like. So don't forget that there are 4 important points in every period. So if that's pi, there's going to be pi by 4, which is 45 degrees. There's pi by 2, which is 90. There's 3 pi by 4. So basically it's pi by 4, 2 pi by 4, 3 pi by 4, and then 4 pi by 4, which is pi. So, and then I could keep going, because remember you're going up in pi by 4s. So then this would be 5 pi by 4. This will be 6 pi by 4, which we would simplify to 3 pi by 2, and then 7 pi by 4, and then 8 pi by 4, which is 2 pi. So you probably are, I'm probably going a bit too fast for this because we're trying to recap radian measure and trig graphs all in the same sentence here. Okay, so let's just quickly try and plot this, just sine of 2t. So sine, don't forget, starts at 0, then goes up to 1, then down to 0, then down to -1, and then back. Now, we stretched this by a factor of 3, and we moved up 1. So if I'm stretching 0 by a factor of 3, nothing happens. But if I move up 1, and it might actually help me to put in some, this is a terribly drawn graph, 1, 2, 3, -1, -2. So let me go back to this. If I stretch 0 by a factor of 3, nothing happens. But now I moved up 1, so it goes to 1. This, if I stretch 1 by a factor of 3, it goes to 3, and then I move up 1. This is 0 stretched by a factor of 3, nothing happens, but move up 1. -1 will go down to -3 when stretched, but then up 1 to -2, and this will go back to 1. So actually, I get this. Now, I could have used my calculator because I could use my table. For your table, you have to know a start point, an end point, and the steps. Now, I know the steps are pi by 4, and I know I'm starting at 0, and I'm hopefully going to end at 2 pi. So I absolutely can use my table, and we will revise trig functions in class. Now, what I'm going to do is just repeat. So repeat, 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 because it's the second period. So continue, down, round, etc. Now, it doesn't say whether I should label my x-intercepts. I could go and say solve that equation, but I'm not really going to bother. So I've sketched the graph. It was just a sketch. That looks very interesting. And now it says determine the times when the particle is at rest. Okay, now when would something be at rest? They would be at rest when my velocity equals 0. That's when your particle will be at rest. Now, don't forget that velocity is equal to your first derivative of displacement. So when is my gradient basically equal to 0 is when my particle will be at rest. Now that kind of makes sense because this graph is representing the displacement of this particle. And so I can see when it's moving. So when it'll be at rest, surely will be these parts here. At my stationary points. It'll be stationary. So basically I do know those already because I drew a pretty good graph. So it's pi by 4, it's 3 pi by 4, it's at 5 pi by 4, and it's 7 pi by 4. Now we could have solved that algebraically. So let me just show you how we would have solved that algebraically. We could have said, here's my function. My function is 1 plus 3 sine 2t. So my derivative would be, well, 1 differentiates to nothing. This would be 3 cos 2t, that's the outside function, multiplied by the derivative of the inside function. So it would be 6 cos 2t. And you would be finding out when that equals 0, which means you will be basically finding out where cos 2t equals 0. And you could shift cos of 0, and shift cos of 0 will give you pi by 2. So basically 2t equals plus or minus pi by 2, and then plus, sorry, I should say 2 pi times k. This is probably weird because we haven't solved trig equations with radians, and so this is quite weird, but basically it's plus or minus 90 degrees, and then plus 360k, which means t equals plus or minus pi by 4, plus now divided by 2 is pi times k. Now don't forget this domain was from 0 to 2 pi. So negative pi by 4 is not applicable, but pi by 4 is, so that's there. And I'm allowed to add pi. So pi by 4 plus pi will be 5 pi by 4. And negative pi by 4 but plus pi will be 3 pi by 4. And if I plus another pi, I'll get 7 pi by 4. So I could have solved it algebraically if I hadn't drawn a picture. So that one was a bit of a weird one because that was diving into radian measure and drawing trig graphs and solving trig equations in radians, which we haven't done. But how fun is that? So that is trig differentiation in AP Maths. Well done.